Some good rules, general good rules of thumb: think parallel. Look at your problem and think, how can I access this? How can I attack this problem with multiple streams of data at the same time? How can I deal with this problem? So you look at the code so it can be parallelized. It's hard to get to sort of, if you have an algorithm in your code and then you want to change that to a different algorithm that is parallelizable later on, that's very hard. So it's kind of important to get these things right in the beginning. And usually when we're looking at data structure and algorithms, we have been trained to choose the fastest single-threaded algorithms out there. And that's kind of something we have to retrain ourselves and look at. Okay, that is probably the fastest single-threaded algorithm, but on the other hand, that algorithm is actually slower if I run it in a single thread, but on the other hand, I can parallelize it. So that if I run it in multiple streams, it's actually going to be faster. So we have to sort of retrain the way we think. Program for tasks. So let's also go back to think about when you program. Don't think about threads when you program. Think about tasks that, okay, this is a task that needs to be done. This is something that needs to be done. Program that, and then you write a dispatcher code that dispatches these jobs into worker threads. It just keeps separate the logic of the code, separate that from the logic of the dispatching. That's kind of it makes the code a lot cleaner and easier to understand what's actually happening in the code. It's actually easier to debug that code, and it tends to get less race condition and errors like that. Avoid locking as long as possible. If you don't necessarily need a lock, you can try to like do implicit synchronization rather than explicit synchronization. And if you necessarily need to have a lock somewhere, try to use atomic operations if possible, right? Most operating systems today, they have atomics, and most hardware have atomics implemented in hardware. So you can do atomic increments, atomic additions, and things like that. So most of the things we need, you used to use like a mutex, or we used to use a semaphore or a basic simple lock to protect some data. We can now do in most operating systems with atomic operations, which means that we actually don't have to protect it with lock anymore. If you necessarily need locking or synchronization primitives, don't go and write your own. I had a case not long ago where I was helping some service, and it turns out that the vendor in this case, long time ago, because they had problem with POSIX mutexes and POSIX semaphores on a different operating system, they wrote their own. So in this case, what they had a spin lock. Okay? So you're coming in here, you try to acquire a lock, you can't get the lock because the lock is held by something else. You start to spin, and they had a spin count. They could tweak the spin count, and after they spun the number of loops, maximum loops they had in the spin count, they did a yield. Okay, what happens when you do a yield? You go to the bottom of the run queue. Okay, and this application, they had about 1,200 processes. That was sharing some resources. In this case, there were about 30 processes that was waiting for the same resource. So these 30 processes, they were kind of looping through the run queue like this, because it was one of these processes was holding a lock a long time due to programming error in an upper level function. So what happens then, because you're spinning, right? And when you're spinning, you're using 100% CPU. So what happened was like you're seeing the CPU utilization was going like up to 100%. And it was just user CPU, no system CPU. So the system didn't do anything. It was only doing spins. And that's because they wrote their own spin lock rather than to use the built-in adaptive lock that we have in Solaris. So what the adaptive lock does, it goes in, try to acquire the lock. You can't acquire the lock. It starts spinning for a number of iterations. Then it goes into sleep queue. It sleeps until the lock is released, and then it goes try to acquire the lock. And it also, there are more things to it than just, but simplifies it, which means that they will actually work. So we've done the homework on these primitives. So use those. They tend to work. They've been in use for about 20 years. And we improved them for 20 years. Observability is king. So use tools that provides observability. So if you're running multi-threaded code, use a good tool chain. And boys, GCC and GDB ain't a good tool chain for that. Sun Studio or Solaris Studio is a very good tool chain for that. It has extremely good tools for observability into multi-threaded applications. One of my favorite tools is the performance analyzer. We have a memory space analyzer. We have a race condition analyzer. We have a locklin tool that basically does a static analyzing of your locking, so you don't have any deadlocks in your code. These are tools that you basically, in the unit space, you get them from Sun Studio, and that's basically the only place. And then you top up that with things like dtrace and MDB, and you have by far the best tool chain. So if you're going to go the path of writing multi-threaded code for multi-core systems, even if you're going to deploy them on the Unix system, do your development on Solaris. Because observability in Solaris when it comes to thread is so much better. By far outshines anything you have on Linux or AIX or HPUX. That's again because we've done this for a long time, or we know what our customers needs. They're asking for these things, and we ask for them. We need these things when we write the operating system. So, what can we do? And we, in this case, is Solaris. What can we do to help you guys? The main purpose of operating system is to write services and abstraction for application code. Right? That's why you have an operating system. You don't have an operation for having an operating system. You have an operating system because you want to use the computer. And to be able to simplify your application code so the application code gets easier. So you don't have to deal with the gory details of the CPU and scheduling and all of those things. Right? That's why you have an operating system. So what can we do? Okay, so what can we do? We have a number. First, we've done it for a long time. As I said, we did systems with 96, 72, 96 CPUs in the late 90s. We've done this for a long time. We've been there, we've done it. We know what's the scales. We have a fairly balanced kernel today because we've gone through coarse grain locking, fine grain locking, which kind of figured out. You always see there's there always is changes, sort of. You're always tuning how you do your locking, but we kind of have a fairly good balance now in the operating system itself. We have a very good scalable threads model. But that's also originally we had what we thought was a very good threads model. It turned out it wasn't that good because it added a lot of complexity. So we had a multi-level threads model up to about Solaris 8, Solaris 9 time frame. Now we have a single layer. So every thread in the application code, always associated with an LWP in the kernel. So you have always a one-to-one mapping between the user space thread and kernel space threads. Simplifies things like signal handling. Simplifies things like scheduling and other things like that. You don't have scheduling inversion and other things. So if you go way back when Java was starting coming out, we had very interesting behaviors of Java on Solaris because we had too many layers of scheduling. So we had scheduling inversion problems where high priority thread in Java came on a wrong thread in the user level threads libraries, and then it came into. So yeah, it was very gory. With a more straightforward threads model, we could simplify it. We actually caught about 90% of the code. So the code that we had in our old threads library was about almost 10 times larger than the code base we have in our current threads libraries. It's much slimmer, much tighter, much faster code. Going back to observability, very good observability tools. And it's as a multi-threaded code is very hard to write. So you need very good tools. I hope that you've been listening to our colleagues from Sun Studio, our studio colleagues, and they help you with other tools. So dtrace, we have what we call the P tools, which is tools that you can use to look at different processes, how processes looks and things like that. And then MDB. MDB is, we talk a lot about dtrace, We don't talk about MDB that much. This is probably by far the best command line debugger you can get in the industry. It is extremely flexible and extremely powerful. And it's very extensible, so you can extend it with new functions, new scripts and things like that, and new macros in it. It's very, 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 very powerful. A good selection of plug-compatible mallocs. What do I mean with plug-compatible? Well, the plug-compatible mean like you just do an LD preload or you do link to another library. You don't have to change your code. But you can actually, so we have libum, mtalloc, we have a couple of more allocs that you can replace. So if you write multi-threaded code, never, ever, 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 ever use the old libc's malloc. We are putting in a new libc, we're putting in a new malloc in libc that actually is very, very good. So the old malloc that we had in libc was based on basically bit tight on memory. So it's optimized for resource, the memory as the gating resource rather, right? The new mallocs that we have now is gating, okay, memory is cheap. We have plenty of memory, we don't have to worry about that. So use lots of memory, get better performance. So the two different sides of sort of optimization spectrum. And the most flexible and the memory library we have, I think, is libum. It adds a lot of functionality. So I'm going to talk about this in a little bit more detail. So threads, it's designed in from Solaris from the beginning. Fully preemptive curl, priority inheritance, the deterministic response time. It means actually Solaris is actually a real-time operating system. Did you know that? You can actually write hard real-time applications on Solaris. And Solaris delivers on that. It's pretty cool. Because it was designed to do that from the scratch. Skip this. So the multi-thread process, so so all kernel threads is where we do scheduling, right? And there's a mapping, also mapping one-to-one between the kernel thread and user thread, which means that we basically schedule all multi-threads. So if you have a multi-threaded process, we don't schedule on the process. We actually schedule on per thread in the kernel. A non-threaded process has one kernel thread and one LWP, and then you have your address space and one pointer and so on and so forth. So simple. A threaded process will have multiple kernel threads associated with multiple user space threads, but you still have just one address space. So you have all these threads in a process share the process context, the address space, open files, credentials, and signal disposition, things like that. It's shared by all the threads. And this is actually turns out to be a little bit of a problem. Makes programming with signals in a multi-threaded process a little bit harder than it actually needs to be. Each thread has its own signal. You have an old signal mask, so you can actually you can do different things with the signal mask, but it still kind of makes things a little bit hard. So what's a thread? A thread is address space shared from among lightweight processes. That's a similar thing. An LWP is a kernel thread. That's what the kernel sees from a thread. You see the data structure in the kernel that then is connected to the data structure in the user space. That was what the kernel sees from a thread. System is a thread has a global priority and we schedule everything in so global priority. Highest priority always wins. We have optimization so that if you're running, we try to keep things on the same CPU, and you can put things in the same process group and things like that. So we try to be smart of where we're executing threads on the system. The user threads, a thread is an entry point in the function, whatever execution path it's doing, right? So it's fairly straightforward. And it says threads live on top of kernel LWP. Solaris 9 and going forward, each LWP has their own kernel threads. Before we had like one-to-one and many-to-one mapping, so it was a little bit more flexible, but it turned out to be, we thought it was a better model, but it turned out to be a worse model, but out of complexity. So one of the cool features that we added in when Solaris 10 came out was something called event ports. So event ports unifies asynchronous event-based programming. So event-based programs are file descriptors, sockets, timers, pipe, asynchronous IDs, and user-defined events. And all of these different types of event-based programmers have traditionally had their own programming model. means that if I want to do this, I did it in one way. If I did this, I did it in one. So if I did signals, I did it in one way. If I did pull, I did it in one way. And so I needed to know that. And if I was mixing signals and pulls and asynchronous I/O, I ended up with a fairly big hairball of messy code, right? So event ports is there to be able to streamline this code for you. You have one set of APIs to deal with any type of event-based programming. So it kind of looks, previously kind of looked something like this, that you did socket data timers and signal handlers, and it was kind of spread all over the system, and it turns out to be very easily turn out to be fairly tricky task to keep track of this. So what event ports then does, it actually then unifies all of these programming models to a unified set of APIs where you as a consumer of event, you can subscribe on an event, you can set up an event, you can subscribe on an event, and you can also terminate it and you can consume events, right? It's much easier, straightforward, simplified. So what that basically means that you move the hard code out of your application, let the operating system and the libraries deal with the hard code, and you get a much cleaner code in your application. A cleaner code in application, less bugs, faster, more scalable. So instead of having all these APIs, I now have 3 APIs I need to do. So I have port create, port associate, and port get. Easy, straightforward. I don't have to care about if it's a signal, it's a select, it's a pull, it's a timer, or whatever. It's the same APIs. Out of time, I think I'm going to move away here. Atomic operations, I think, is one of the nicest things. So atomic operation are now provided as part of libc. We used to have it as a separate library before. It's part of libc, and it basically using the same atomic operations that we use in the kernel, just the user space implementation of that. It then relies on the atomic operations that you have supported for in the hardware. If we don't have support for in the hardware, we usually create we use memory barriers and so on and so forth to create what looks for you as an atomic operation. But for most current CPUs now, they have support for all of the atomic operations. But if you run on some legacy old CPU somewhere, we can basically emulate that in software. So a traditional piece of code might look something like this. I create my mutex, so that takes a little bit of space. I then acquire my mutex. I increment my counter. This is pretty common now. It's so much code out there that has this exact function. You just have a mutex. You just do a counter plus, because this counter happens to be shared between many threads. So this was the way we did it. Using atomic operations. Easier. Like you don't have to initialize your mutex, you don't have to query the music, you do an atomic add and increment your value with 1. And by the way, you can do more things. You can do multiplication, division, subtractions, and a few other things as well. So you can look at that. We have, if you look at atomic ops and man page, you can see the different functions we have. Most cases, you can actually get rid of a lot of locking, a lot of mutex in your code by using atomics as a replacement for mutexes. libuman, one of my absolute favorites. It's one of the best things, I would say, even prior to the existence of sliced bread. So I think it's actually better than sliced bread. I don't like sliced bread. Okay, I like to cut my slice myself. So this is about in 96, 97, we implemented a new memory allocator in the kernel called a slab memory allocator. And this is basically just a user space port of that slab memory allocator. And we have one customer, you might know about him, he's fairly well known in the open source community called Ben Rockwood. He likes libuman so much, he's actually ported it to Linux. So you can actually get libuman on Linux. It has so much functionality, so much rich functionality. It's performed exceptionally well on multiprocessor systems. I say it's fairly wasteful when it comes to a memory usage, but anyhow you get very good scalability. Link application directly, or I use libumem a lot of times for debugging to find memory leaks and other things. So again, then use LD preload just to preload it in front of what the actual linking is, and I can then just plug it in as a replacement instead of malloc. It has logging facility, so you can actually log your memory accesses. So it sets up automatically if you're allocating a memory area, it sets up a red zone in the ends of that memory area. So it will log accesses outside in the red zone rather than the core dump, rather than do zigzag. Critical information for each transaction that you can get in stack traces, high resolution, time-sensitive trade ID, and so you can set a different levels of how much data you actually want to log. If you want to log everything, you can basically know exactly what microsecond it was accessed, exactly from where from, and what data, and so on and so forth. So you can get a lot of information. Human debug, you can use different things like buffer overruns, multiple frees, use of uninitialized data, use of freed buffers and things like that. You can log those, and you can get debugging information out of those things. So application, rather than to get a zigzag, if you have a buffer overrun there, you do a abort of the application. You stop the application, which means that you have actually a really, really good. You still have the memory image of the application that you can use a debug, attach a debug to, and you can look into memory application. And then comes one of the best things. So libumem and MDB is kind of tightly connected like this. So there are macros in MDB that will actually use the logging and debugging information that you have from libumem. So MDB has a macro called find leaks. Very, very useful macro. You just set up logging and things like that. Then you start MDB onto that process. You type : find leaks, and you will actually get a list of potential leaks in your application. Very useful. libumem is also, so for best performance, you can use, libumem has an extra set of APIs that you can use. So you can use it for allocating and creating buffers, creating caches, kind of like we have in the kernel. So we have pre-initialized data structures in a cache, which means when you go from your application, you want a data structure, it's already there, it's pre-allocated in a cache. It's much, much faster than to allocate, do malloc, get the data, initialize the data, and initialize the data structure, and then use it, right? Here you have a structure that's pre-initialized. Yeah, please use it. libumem, if you have short-lived processes, libumem is a bad idea because it takes startup sort of cost to sort of get the good advantages. And don't forget Sun Studio. Solar Studio is a superb set of tools. I think I mentioned it a number of times now. It's I personally kind of think it's actually probably the best toolchain in the industry to write multi-threaded code. It's very, very good for those things. We have race detection tools, performance analyzer, compilers automatic prioritization, and many, many more things. And I said, don't write multi-thread code without it. It's like usually don't leave your house without it. And if you're writing code on both Solaris and Linux, you can actually use Sun Studio or Solar Studio on Linux as well. So we have it on both platforms. Although some of the observability tools that we have are only available on Solaris because we're relying on features in the Solaris operating system to actually dig out the information from the kernel. Summary: Solaris 10, Oracle Solaris 10 is the premier operating for the multi-core world. Yes, because we've done SMPs before, and a multi-core system is just, from an operating system point, it's an SMP. It's multiple CPUs with lots of memory. We know that. We've been there. We've done that. Proven scalability. We have done this for 10 plus years. Large system in this range. Even though we're going bigger now than we've ever gone before. I don't think we ever had a production system with 512 CPUs before, which we're going to have later on this year. But if we've done 128, we've done those type of systems in our labs previously. So it gives you the tools you need to create the right great scaling applications. Observability, it is so important. It's so important to be able to see what's actually going on in the system, to see what the different threads are doing, to be able to observe what's happening. Because you're going to have race conditions, you're going to have locking issues. And we provide the tool in the operating system for you to find those problems. And we have Brian here as well. It's also a very, very good tool, by the way. Old Unix-style code can be made to scale fairly well. You won't scale as well as a multi-threaded code, but you can retrofit old code bases, so you don't necessarily have to throw everything out and start from scratch, right? You can retrofit it and going kind of what I call the hybrid model, where you're sort of looking at your code and you see where does it make sense to multi-thread parts of my application, and where can I actually use the single streams, single-threaded application, the single data streams application I had before, and put that and basically just use multiple instances of that instead as one way of scaling. And the modifications that you need to do are they tend to be fairly minor. It's like order of magnitude less than rewriting your application. And thank you very, very much. And I have 1 minute and 26 seconds. Thank you very much. Time for Brian soon. I'm actually not going to have time for questions because I have to rush to my next session.